Hello, my name is Peyton Kaufman and I am working on the crusher portion of the JCATI Delaminator project. The project hopes to improve upon the previous year's design by improving the crusher's delamination performance while crushing Boeing 777 composite material while achieving a feed rate of material of 1 foot per minute with 100% reliability. This picture shows the initial concept for the redesign, featuring large driven gears instead of the stationary hydraulic crusher that was there prior. There is plenty of engineering merit in this project that will allow me to spec components and perform a wide variety of load analysis to perfect the design. Due to there being minimal information on the properties of the composite material, energy analysis was performed on the hydraulic crusher system using the known pressure of 20,000 psi and the measured height of the crushing teeth, which were assumed to be equal to the displacement of the composite under load. However, when performing gear design analysis, this design was found to not be feasible, as the crusher would need to be made from solid steel to survive the assumed loads. Then again, these issues could stem from the gear analysis being performed on a part that is gear-like, but not really a gear. In the end, this analysis was scrapped, and a torque limitation of 3,100 inch-pounds was set as the max torque output by the electric motor drive system. So, the design of the shaft was the most critical part of the project, and the shaft would need to withstand the torque in addition to varying levels of shear and bending. And the design of the shaft will determine many of the other parts of the project. First, a general diagram was created with key positions and their distance along the shaft labeled A through D. With the torque on the shaft known, analysis can be performed to find the loads on each critical section of the shaft. Section D required calculations using the torque, the size of the gears, and the standard pitch angle to determine the tangential and radial loads experienced by both the gear and the shaft. Next, location B requires much of the same analysis, except it utilizes a pitch angle that was found by analyzing the crusher model that I had created in SolidWorks to determine these loads. Using force and moment equilibrium in both the X and Y directions, the various loads could be determined at the bearing locations. After you found all the reaction forces along the shaft, a shear and moment diagram was made for the shaft in order to determine the overall shear and bending moments experienced along the shaft. This data was, these loads were put onto a table and then put into a spreadsheet to help design the rest of the shaft. So this particular shaft will be using 1020 cold rolled steel in order to get very practical minimum shaft diameters for this project. With the minimum shaft diameters determined, the bearings needed to be spec'd for the shaft locations A and C, which would be around here and here. Due to the loads at these locations, the flange bearings with inner diameters of 1 3/8 inch and 2 3/4 inch were selected to support the shaft, which would increase the shaft diameter at these locations. In addition, to keep the stress concentrations caused by the steps below 2, which was used in the design factor, or the lowest stress concentration factor for the shaft, in order to keep the stress concentrations caused by the steps below 2, figure A18-6 was used to determine the radius of the fillets that will be machined at these locations. Many issues came up during the construction process. Many of the problems branched from organization issues and not double checking how everything was supposed to fit on the SolidWorks model. So the first issue was the incorrect bearing size. I knew the size of the shaft of the location was supposed to be 1 3/4 inch. However, when browsing parts, I had put a 1 and 3/8 inch bearing on by mistake onto the parts list. I guess I forgot to read past the 3, and however, fortunately, 1 and 3/8 was above the minimum diameter for that section of shaft, which was 0.707, and it could be machined to the smaller diameter to fit the bearing. The next mistake was the bolt spacing. This stemmed from the bearing size. Having a smaller bearing meant that the side plate that I had sent to plasma cut had different bolt spacing than what could be used by the smaller bearings. So new holes for the bolts needed to be drilled into the plate to accommodate. Next was the side plate size. Initially, it was intended to fit within the scope of the previous chassis, which only had a height of around 9 inches. However, since the bearings were not placed on the SolidWorks model, there was interference due to the shaft spacing with the large flange bearings. So the side plates in the crusher had to be completely redesigned and made larger to accommodate these larger bearings. Other manufacturing issues. Many parts were outside of the scope to be machined by the shop at CWU, and so there was outsourcing that needed to be done, which increased the time spent and costs. Another large risk was taken with the crusher, which the initial or current design relies on welds to weld the angle irons to the discs. And with the welding area being out of commission and not being made accessible until recently, burned a lot of construction time and really dragged the project back. Construction summary on new parts. So the new design hoped to use as much of the previous design as possible. With the frame could be completely reused with some modifications to increase the height by adding another angle iron and bolting it on. The top plate only needed some additional milling to accommodate the crusher, but other than this, construction consisted mostly of using the horizontal cutter to cut angle irons to length and determining shaft diameters in order to machine or shaft diameter coordinates to code the CNC properly to aid in machining the extremely large shaft. Testing the feed rate requires that 1 foot of material be inserted for each trial, and the time that the material takes to get through the entire system be recorded. While testing has not been completed as of right now, here's what I expect the results from testing to be. Overall, I expect there to be much lower feed rates than the stated requirement of 1 foot per minute, and this is likely due to slipping of the material as it passes through the system, and this is likely caused by the crusher tooth design. The lamination is largely a qualitative assessment, and overall I expect this plywood would separate its layers completely, and that the composite material have very little separation in comparison due to the lower loads caused by the torque limitations. As expected from a project that was plagued by issues, the Gantt chart initially created to help budget time was difficult to follow. These X's indicate that time was budgeted rather sporadically and likely contributed to the organizational errors that plagued the construction and testing sections. This project was very expensive. Half the total costs were taken up by the huge steel round rods that were needed to machine the shaft, in addition to the very large bearings that were needed to support them. Without the funding donated by JCATI, this project would not have been possible. If there are any specific questions, feel free to contact me at the phone number or email here. Thank you all for listening.